rational curves and rational homogeneous manifolds.
Thank you very much. So I would like, firstly, I would like to thank for this opportunity to talk here and for the invitation to Moscow. I'm very happy to be here, and I'm very glad. I've never been to Moscow at this time of the year, so I find it very exceptional and beautiful. And having said so, I will use this occasion to shamelessly advertise our, Polish entertainment, that is school. Each year in September we organize schools which are directed at the graduate students. And this September we organize, this will be 38, so imagine, 38. So I bet that some of you weren't born yet. So this is the 38th school, and the topic will be Cox rings. This is the second week of September, so I think will be 6 to 12 September. And the teachers will be Jürgen Hausen, Antonio Lapace, and Simon Keicher. And okay, if you want to register, then go to this web page. So this is agvs.mimuw.edu.pl, and we provide the graduate students with accommodation. We don't pay for travel, but we will be very happy if the graduate students come. Okay, there were the occasions where we had guests from Russia, from Moscow, and we enjoyed it. Oh, okay.
There would be Warsaw.
No. Oh, that's the good part. Thank you very much. That's the good. No Warsaw. Okay, so that's on the seashore. The place of the name is Łukęcin. So this is about 100 kilometers from Szczecin, and it's very hard to get there. But this is like 500 meters from the sea, and in September the sea will be, well, of course I can't promise warm, but well, well, not that colder than usually. Okay.
Bring bicycle and just bike there.
Yeah. Okay, so that's the advertisement. I hope that it will somehow convince some people to come. And now about the talk. So I should say at the beginning that this is like a project which I did not start. I mean, I worked on a similar subject some time ago, but then eventually the project evolved in different configurations by the following people. So Roberto Munoz, Gianluca Occhetta, I think he has double C, or maybe one, sorry. Don't tell Gianluca that I don't remember how many C he has. He has double T, I think two. Okay, Luis Sola Conte, and I forgot the accents. Kiwamu Watanabe, and at some point I joined the team, so it's, well, different configurations. And the topic, let me write the title again, so this is rational curves and rational homogeneous varieties. And in some sense, in the last 10 minutes of Jason's talk, there were this somehow hint that in some cases, so in the case of homogeneous spaces, the families of rational curves can be well understood, but this makes reasonable question if the rational homogeneous variety can be reconstructed either from the properties of general curves or from other geometric properties. And the talk will be about this, but since I was told that this is supposed to be like the introductory talk, so I will start with recalling what are the rational homogeneous varieties about, which is important because in the end, if you want to reconstruct them, then somehow the reconstruction will be obtained by reverse engineering. So let's try to understand how they are constructed first of all. Okay, so firstly, we work over C. And well, all varieties, unless otherwise stated, will be projective. And well, if you think about homogeneous varieties, then there are essentially two classes under these assumptions. These are either abelian varieties, and I don't want to talk about them, or rational varieties. And this will be the topic. And a descriptive manner of setting the whole stage for this class is just to start from the group, and I'll follow the this pattern. Usually, I prefer to think about the case that X is not a product, but you can easily erase this assumption. Okay, so then under these assumptions, such X will be a quotient of some simple group. So G is a simple algebraic group. And P is so-called parabolic subgroup. So here, among the parabolic subgroups, so those which give rise to rational homogeneous varieties, you have a distinguished class of groups, namely the Borel groups. And this can be a class, described not only as a group which gives a quotient which is projective variety, but this is also the maximal closed solvable subgroup of this original group G. And actually there is this, I think it's due to Borel, characterization of parabolic subgroups, that parabolic subgroup, so the subgroup which is the isotropy of the point under the action of G on transitive action of G on a variety X, every such group has to contain a parabolic subgroup. Okay, so in some sense, Borel group is the smallest among all parabolic subgroups. Okay, well, usually I will follow the same pattern. Usually there is this example which you give. So you start with the G, which is SLN over C. And as you see, well, this is not quite simple, but up to a finite subgroup, up to the center, it is. So there will be this ambiguity that I will usually refer to semi-simple groups instead of simple groups. At any rate, so you represent them as n by n invertible matrices of determinant 1. And then the Borel group usually is described as the matrix of the upper triangular, as a subgroup of upper triangular matrices. So if you have the diagonal, then everything on the diagonal and above the diagonal is possibly non-zero, and what's below the diagonal is zero. And actually, this is related to a choice of a flag. So if you think about, let's change the dimension. Let's think about SLN plus 1. So if you think about the vector space Vn plus 1 as the vector on which this SL acts, then you have a flag. So that's the zero-dimensional V1, etc. Okay, so that's Cn plus 1. And if you choose the flag according to the choice of the basis in which this matrix is written, then this is the isotropy group of this flag, and then this variety G over B, in this particular case, is the set of all flags. And of course, as I said, this is the special case in which this group is bigger. So you may think about the set of non-complete flags, and as the result, you will obtain a variety which is of smaller dimension. And I want to, so there are two particular examples. Okay, it's here. Now I should think very carefully how to organize the blackboard, so I will erase which is not needed. Okay. So there are two other examples which I want to point out of homogeneous varieties. So these are the Grassmann varieties. So they are very poor flags. You just choose one element in between 0 and the whole variety. And varieties of the type G over Pi, where Pi is different from B. So this is a bigger subgroup, but this is smallest among those. So in particular, if you look at this picture, then the smallest possible subgroup which you can think about is you choose these elements on the diagonal, you put zeros here. These are things which are non-zero, and you just throw in one more element in this parabolic subgroup. So these are non-zeros. So in these terms, it means that you just make your flag by throwing in just one element. And this gives you also an example, a typical example, of a map between the homogeneous varieties of this type. Namely, you have the projection from this G over B, which goes to G over Pi, and this is just a P1 bundle. You will get convinced very easily if you think about the case of flags. Okay, so this is just an example, and of course you have the whole bunch of them, but not that many. In particular, you have all classical groups, which can be represented like over here, but they are associated to some symmetric or skew-symmetric form. So that the SO n plus 1, well, I'm usually confused with the odd or even. So what I will do, I will just denote them by letters. So the SO case, I will call just B, N, or DN. And the SP case I will call just Cn. And explanation is because of the Dynkin diagrams, which you can associate, which I will just handle in a moment. So the SL case is the AN case, and you have a few exceptions, which are E6, E7, E8, F4, if I remember correctly, and G2. Okay, so that's the very general introduction, but if you want to understand the geometry of these objects, you usually go to the algebras. So let me recall this part as well, because it will be important for this engineering that I promised will take place soon. Okay, so the Lie algebra of the group G will be denoted by the, well, Frankfurt font G, and we have the Borel decomposition. Namely, you can write this G as a direct sum of H, and G alphas, which are constructed in the following way, that H is the so-called Cartan subalgebra, so this is Cartan decomposition. So in pure terms, this is associated to some torus which lives in, so this is algebraic torus. And this decomposition comes from the action in which these spaces, this G alphas are one-dimensional spaces one-dimensional eigenspaces associated to the adjoint part of the torus action. Okay, and this R stands for the set of roots. And of course, they are the eigenvalues, so they live in the Hom H C star, which I will shamelessly identify as a lattice in the dual algebra, in the dual space. Okay, did I forget anything? Now, for those who are already bored, I think I'm already at the end of the first page, and then I will make it somehow quicker. Well, okay, the first part of the page 2 will be also maybe somehow redundant for some people here, or for most people here. Okay, then the choice of the Borel group is associated to the division of this set of roots into the two parts, and usually it is explained in terms by a choice of some character living here, so that you have this division realized. And so here you have a root which I will call alpha, and here it's opposite, and you can realize some copies of SL2 algebra just by taking the G alpha, G minus alpha, so that's the algebra spanned by them, and by the commutator, which lives in the Cartan subalgebra. Okay, and if we look at this example, which I regretfully already erased, so that was the example in which I have this map from G over B to G over Pi, and you can see a special choice of these G alphas, which somehow makes this square matrix of SL2 inserted in this. Well, okay, I'm somehow making more or less obvious identification of the group G and its tangent Lie algebra. Okay, one more thing which I'm supposed to tell among all these general things is that you have the Killing form. And the Weyl group. So I don't want to define the Killing form. At any rate, once you have the Killing form defined, you can define the the Weyl group, which will be the reflection with respect to the hyperplane, which will be orthogonal to two roots. So I choose a root, and then I define the sigma r of V as V minus, and here I should use the K V alpha over alpha time alpha. Okay, so then these numbers here, sometimes they are denoted just, that's the K, where K is the Killing form. These numbers are just denoted by the V alpha. They are non-symmetric, as you see, because of the denominator here. And using these numbers, you can define Cartan matrix. So this is the matrix in which, say, in the Aij place you have this Aij place, you have the, I forgot something. Okay, so if you choose the positive roots, then you consider simple roots. It turns out that there are exactly as many simple roots as the rank of this, or the dimension of this Cartan algebra, and they generate all positive roots in the additive form. So they are the generators. So an example of a simple root is over here. I mean, the extension of the Borel group to the minimal parabolic subgroup containing the Borel group is gotten by just throwing in one extra simple root. Okay, and then the Cartan matrix associated to group, and this is where I refer to the Dynkin diagram, is just the matrix with entries which are the intersection in this way of the simple roots. So alpha I, alpha j are simple roots. And then out of this you define the Dynkin diagram. Where the vertices are simple roots. And the edges are associated to these intersection numbers. In particular, there's no edge, there's a empty edge if this intersection, if this is 0. There is just a simple edge if the intersection is 1, and the possibly double or triple edges directed from the bigger to a smaller root in terms of the Killing form. Okay, that's the first page. And some of, okay. I defined this reflection and the Weyl group of associated to a simple Lie group is just the group generated by reflections. So this is the group of isometries of H of the Cartan algebra generated by these reflections sigma alpha, where alpha are either all roots or positive roots or simple roots. Actually, if you take simple roots and you consider something which is dual, so you define the Weil chamber. So this consists of these elements in H, such that H, the intersection, say in the killing or whatever, because this is just rescaled, is bigger or equal than 0 for all simple roots. Okay, good. So that was, say, 10-minute, maybe more, recollection of the basics of the group theory. Now I'll pass to geometry, okay? So the idea is, well, this is a spoiler, but I will tell you that essentially the idea is having a variety, a disguised homogeneous variety, to find out that it is a homogeneous variety. So in other words, if you have a variety whose geometric properties are like those of a homogeneous variety, you want first of all to find a group and to find this presentation G over P, right? So, so these are the features of homogeneous varieties which will be used to guess which group we are supposed to choose and how to reconstruct this homogeneous variety. Okay? So now, if I take the homogeneous space, the one which has somehow the richest geometry, so G over B, then the first observation which will link this apparently pure algebra to geometry is that the line bundles over this object can be constructed in a way which will be associated to the space of weights of the torus. This is because of the properties of B, namely the characters of B are exactly the characters of H, of this maximal torus. And in fact, if I take a character, say chi, then I can associate to this character a line bundle, say L chi, and this L chi will be just obtained by taking the B times C, B times C, G times C divided by B, where this action of B on G and say T is defined by the character. So on G it acts from the left hand side, so this is B the other way, B inverse, and on T it acts by the character chi of T chi of B times T. Okay, it's better. Okay. And so from a character, so one of these objects that we run into vaguely having this short presentation, we can reconstruct the geometric objects. So line bundles. And it turns out that actually you can make the identification. Now I'm supposed to erase something because I want to make the translation from the group theory to geometry, starting from easier things and building up to somehow more complicated things.
So now I guess G is simply connected, right?
I'm sorry?
G is simply
Yeah, I mean, I'm vague about this. Yes, yes. I said that I use the word simple, but as a matter of fact, I prefer simply connected, right? Yes, that's correct. I'm sorry, I should have. Okay, but there will be more places where I will be ambiguous. Not to. Okay, so the first observation is that once we have this this G, okay, so this is the G and this is the G over B. So this is algebra or group theory and this is geometry. So the first thing is that the characters R of H are associated to line bundles over G over B. What order did I have? Okay. Right, so in particular, I said, well, maybe I didn't say so, but the point was that these characters were, they were a priori living in H dual, but as a matter of fact, they lived not in the complex space, but in the real space, which I will call just E. So this is a lattice spanning the vector space of dimension, the real vector space, associated to the, well, you already believe that I have the appropriate number of generators, so, okay, so in particular, if you take this vector space E, so this is, say, the real span of characters of, and therefore of weights, then if you take line bundles over G over B, then you construct the space of N1 upper X, which is by definition the Picard group, well, divided by whatever, but here we are in a very particular case, so numerical equivalence, linear equivalence are the same, and multiplied by R. So this is just the simple R extension. Okay, and then what you usually say is, once you are in the realm of more ethereal or minimal model program, then you usually want to understand the Neff cone. And I don't know how specific about the definition of the Neff cone I'm supposed to be, but at any rate, so this is the closure of a cone which is generated by ample classes. So this is cone, and here are ample classes. Well, the answer is that under this association, this is just the Weil chamber. I'll explain this in a moment, but just to make an indication that this should be the case, then remember that on the left-hand side you have the whole representation theory. So if you want to classify irreducible representations of this algebraic group, then you choose the maximal weight of this representation which lives in the Weil chamber. So we choose a character which lives in the Weil chamber. I didn't make the name for the Weil chamber, but who cares? So I take the Weil chamber, a character. Okay, then you have the representation, so let's call the representation V lambda, and it turns out that this representation is actually the space of global sections of the line bundle associated to this character on this level, where we are over here, and therefore you have the morphism associated, the character is chi, so that's chi, associated to G over B. So this is just the evaluation of linear sections, and this morphism is G equivariant. Okay? So in particular, if you want to understand different morphes of G over B, you just look at the representations and you look at the closed orbit, which is the image of the G over B under this evaluation morph is associated to some characters. Okay, so if we believe in this, then in particular, we should notice that at some point I said that the faces of the Weyl chamber, well, on this there are just the faces, and here there are extremal contractions. Well, usually when you talk about the Mori theory, then you say about extremal ray, but here we talk about the dual object, so not the cone of the one cycles, but the cone of the devices. Therefore, the word extremal is somehow dually to be associated with the face of the maximal maximal dimension. And remember that these faces were supported, so they were supported by those simple roots. So we had these simple roots alpha I, and guess what? They are associated to the maps G over B to G over Pi. And the fibers, what are the fibers? These are the P1 bundles, as it turns out, similarly as in this SLN case. Here, remember, I constructed a subalgebra associated to a simple root consisting of, what was this? G alpha I, G minus alpha I, and the commutator of these, and I vaguely tried to convince you that from this you will get something which should be tangent to a P1, and these are the fibers. Okay. That's not the end, so I will have to use this. So on this side we have had also the Cartan matrix. So there should be something in here. We already identified the fibers of this morphism, but a part of the fibers, dually, we have the relative canonical bundles. So let Ki be a relative, so this is K, G over B over G over Pi. Okay? Then it turns out that the Cartan matrix is associated to the matrix of intersection, and now I'm always confused. So up to transposition, okay, so this is Ki, and this curve will be called gamma I. Ki intersection, this is the standard intersection, and you are supposed to put minus, because usually you write the Cartan matrix with positive diagonal. Great. Okay, so here it is. So now the expectation is, if you want to make a geometric statement about rational homogeneous varieties, so you want to claim that something is on the left-hand side, then you choose the properties from the right-hand side, and you want to classify those things to recover the rational homogeneous variety on the left-hand side. Well, so in particular, and this will be the main theorem of today, but let's first formulate this thing. So in particular, we have noticed that, so this is corollary from what we said. If I take G over B, okay, so this is smooth projective, and moreover, firstly, it is Fanon, and external contractions are P1 bundles. Well, these are some of these lines which are already posted. Okay. So the task will be explaining that it goes the other way around. Actually, you can release this assumption. So in fact, it is enough to assume that it has so many P1, not bundles, but smooth fibration. So I don't want to assume that this is P1 bundle in Zariski topology. So many such that the rational curves, which are the fibers of this P1 fibration, generate the Mori space of 1 cycles. Okay? But I will stick to this easier formulation. And
Can you avoid one assumption?
Yeah, but not today, okay? Well, okay, so this is one of the versions of the theorem, so I try to stick this to this. So the stronger version is just to avoid Fano. Just think about the appropriate number of P1 bundles so that the fiber generate the Mori space of 1 cycles. Then the classes generate the space of 1 cycles. And maybe a comment is needed. Well, actually, I told you that there is this relation with what Jason said. So, rational homogeneous varieties are special, and as it was noted, there is this Mori theorem, which relates the ampleness of the tangent space, well, with a simple description of the most homogeneous variety, which is the projective space. And actually, in this direction, there are several results. So there are classical results regarding the quadric. There are some results regarding the structure of Grassmannians. There are results of Huang and Mok regarding the recovering rational homogeneous variety, so the type of Grassmannians from the VMRT, so the space of tangencies of minimal rational curves on these varieties. But there is this conjecture, and Frederick will be called upon again by Campana and Peternel. Let me write this. So Campana, Peternel conjecture. Which is as follows, that if Tx is Neff, I will not dwell in explaining what's Neff, so this is a much weaker assumption than the X is G over P. So in some sense, this theorem, which reverts this statement, deals with a very special case, again, as these dealt with somehow the minimalistic case when the Picard group is the smallest, and they use rational curves. But this one, well, maybe I'll state this result. Now I have to be clever and erase the thing which I don't want to have. So the theorem is as follows. So X smooth, well, let's make it this way, Fano, and all, and I will not prove it. I mean, if you assume that this is P1 bundle, this is essentially using the fact that you can choose always a generator, say L, such that the push forward of L equals some line vector bundle E, and then such D is essentially, okay, it makes only sense if D has negative intersection with the gamma, because otherwise this thing has negative, the whole thing has negative intersection with the fiber, and the push forward is just 0 on both sides. So a sketch of the proof is as follows. So you choose L in the case of the P1 bundle such that this holds, and then you know that, say, for any divisor V, you can write it as the L, say, RL plus pullback of something, say, L prime from downstairs, and then you remember that the push forward of the RL is symmetric of this E. And then you make the computation for both sides and you check that they agree. Okay? Essential. That's the more or less idea. In case if this is smooth vibration, it's slightly more complicated but doable. It's not that hard. And the color, which is the second.
All P1 smooth vibrations are P1 bundles?
No. No. Regretful. Well, no. I retract the word regretfully. I mean, without.
I mean, automorphisms of P1 are the same as automorphisms of the corresponding.
Yeah, the abstraction is like in the Brouwer group of this variety there. Let me not discuss it, Misha. Well, okay. Okay, corollary. I hope I have it right. Okay, so situation as above. Then HI XO D plus D gamma plus 1 times K equals HI plus okay, this will be a bigger print, so this is I plus signum, so the sign of the intersection D gamma plus 1. So this is either plus 1 or 0 or minus 1, okay, depending on the sign of this intersection. X O of D. So the trick is, as you see, that here on the left-hand side we have this operation which looks very much like the reflection with respect to something which is perpendicular with respect to K, while on the right-hand side we have shift by 1. And the idea, I made the computation on my paper, so I can show it, but idea of the proof is more or less like this. So you want to prove that these two things are together, so say you take the I'm sorry. You take the right hand side and you assume that this intersection intersection of D with the fiber is positive, then the cohomology, whatever it is over here, is the cohomology of the push forward. And then you use the fact that over X you have the Serre duality. So essentially it changes the cohomology. I goes into I, n minus I. Here we have the push forward, which allows to calculate the cohomology of line bundle here, provided that the intersection with gamma is positive down or Y. And here you have the Serre duality, which now changes I into n minus 1 minus I. So we have shift by 1. Okay? And this lemma allows you to identify, to compare the push forward before and after duality. So if you run all this way, then this is the difference, is exactly the shift by this and the shift in the exponent over here. Do you want me to calculate it? Okay. Should I calculate it? Yes, okay. I will. I like it. Maybe I'll get something wrong. Okay, so I'm computing this is small I, right? Because I want just to compare the numbers, not to claim that. So I'm calculating over X O of D, and I want to assume that D dot gamma is negative, which does not really make any difference, as it turns out. And this is the same. Well, I will just copy because I don't want to get confused. So this is over X. This is the duality. I'm using also the fact that Kx equals the pullback, which I will just omit, of Ky plus K, right? Where K is the relative. Okay. By my notation, this is the relative. Okay. So. Sorry. So this is Kx minus D, but I can rewrite it K minus D minus Ky. I'm assuming that this is negative, so I can use this push forward. So pushing forward, I will obtain this is the pullback from Y, so I will get here X push forward K minus D, which is fortunately the thing which I have over here, right? Minus Ky. Now I'm using and minus E. Now I'm using my lemma to get that this equals Hi minus 1 and Y push forward. I'm supposed to rewrite this thing here, and now you see how, I'm sorry, but I will not squeeze in here. So this is, instead of this, from the lemma I write. Okay.
What you're proving now is
I'm proving this thing. I'm proving the color. Okay. And again, by the assumption that this thing on the right-hand side has the positive intersection with the fiber, this is exactly what I claim over here. So this is left-hand side. That was right-hand side. I didn't cheat. You can verify it easily. Okay. Now, I claim that this essentially boils down to proving the first part. Now I'm supposed to erase something. Because what I do, I define I can think about this operation which is over here. So D goes to D plus D time gamma plus 1 K. I can think about it as an affine reflection. Okay? And repeat the argument which was essentially in the construction of the Weyl group. So, of course, the only drawback is that I will have to take affine reflection, but Otherwise, I can make the shift as I explained and think about the cohomologies. Well, I mean this type of reflection, right? And this thing is the linear reflection plus a shift. So here I have the plus a shift of k. Okay, then I take the group generated by these things. Okay, I can, on N1, upper X, we have a group which I will call W of X, generated
By your reflections. And, how you define your reflections again?
here. This is a linear, I mean, I don't have any product yet, but this is merely a problem. I mean, D is mapped to D plus a multiplicity of K, which is K for this P1 bundle, but I'm starting,
So it's relative k with respect to this P1 bond.
yes. Okay, now I'm using the lemma for each of these. So I'm in the situation of the theorem. I'm not organized, I'm sorry. I have a number of these extremal contractions which look like this. For
Should you interpret these reflections as reflections in that category with respect to X?
Don't ask me now. Perhaps yes. Yes, yes. I bet you can.
Stupidity Kuznetsov just left.
Yes, I'm sorry.
He's late for his training. So.
Yeah. Yeah.
How about calling one, please? Can you
Once more.
calling one, please? Can you write down the same formula? Suppose your phi is just calling one, not Q1 bundle, but calling one.
This is the problem. I mean, I don't think you have this thing.
But anyway, you can write down the solution, right? And it will be
You can write like this, but I will use just in a minute that the cohomology behaves nicely. Okay, I mean, formally, I can define it whatever. I mean, this is just something, right? But now I want to claim that due to this lemma, I can control the cohomology. First of all, on the Neff cone, if D is a Neff, then H0 is the only non-zero cohomology. Here, for example, I can use the assumption that this is Fano, right? And Kodaira vanishing theorem, right? Since minus kx is ample, right? So, in particular, that's the first observation. Second observation, which I should put somewhere here. I don't need this general lemma now. Which I will apply there. The chi of x of d is 0 if the intersection of d with some of these gamma i's equals minus 1. That's obvious, right? But if I take the group generated by reflections, the same thing will hold for the composition of reflections. These were just reflections which generated my group. So,
You mean for any I? If for all I it's -1 and then?
no, just hold on. This is for every I, yes, because this is a P1 bundle, and if I have a line bundle which on the fiber of a P1 bundle has intersection -1, then the cohomology vanishes. Yeah, I mean, if I take the push forward, then every push forward is 0, right? So then this is the property, okay? But this will hold also for the image of D via this lemma which controls the cohomology under any composition of these reflections, right? So in particular, from this, it follows that chi of well, the K is not a character anymore, so the Euler polynomial is 0, so this vanishes on hyperplanes defined by reflections. Right? So, okay, I'm vague what I mean the hyperplane. This is not a linear hyperplane, but a fine hyperplane. So modulo this shift of k half is actually, I should, well, this should be of k half, right? Then I can talk instead of affine reflections, I can talk about linear reflections. Okay, so in particular, the number of reflections in this group W is finite. And actually it is equal, well, it is smaller a priori than the dimension of X. On the other hand, this group preserves the lattice, the Picard lattice, which is inside of this n upper 1x. I'm simplifying things a bit, but generally the idea is that you want now to use the classification theorem of reflection groups generated by reflections.
I'm sorry, it is not clear that reflection preserves other mirrors.
Once more.
It is not clear that, well, to understand that something is a reflection group, you should have a reflection that acts on the mirrors of the reflection. Then, you should be preserved.
Yeah. So yeah. But look, this lemma which erased, I can use inductively. I mean, for the composition of reflections. I mean,
What does it do for composition of reflections?
I'm taking the group which is generated by these elementary reflections, okay? And for the elementary reflection, I checked how the cohomology behaves. Then I'm saying, if I take the composition of reflections and it is a reflection, then I have exactly the same property. Right? Essentially because via a number, well, this is like if you would take a face of this Neff cone and transfer it via the group action to another hyperplane with respect to which you reflect. And that's generally the idea, right? I mean, any reflection is a composition of some element of the group with some reflection which is generating which is the face of this Neff cone. So inductively, I'm proving that the cohomology behaves well not only with, I mean, this lemma which I just proved holds also for the reflections which are not only with respect to the faces of this cone. Okay. Okay, where was I? Okay. Now I want to say that since this that by the classification of groups of reflection, since this is the crystallographic group, it preserves the lattice. It is within the Weyl groups of some G. Okay, still, we don't have enough information, for example, to infer that the dimension of this variety X is actually the dimension of the variety G over B. But we can use the Serre duality first of all, to identify that minus kx is this 2-row vector. And secondly, that the dimension of x equals to the dimension of g over b. Which follows because, well, we have this inequality, but on the other hand, we have this reversion of the cohomology associated to the seriality. So the longest element in my Weyl group of G over B must be associated to the seriality. Okay, and the longest element, the length of the longest element is exactly the dimension G over B. Okay, so therefore, since we control the cohomology of X and the seriality of X, we infer that actually we have this isomorphism. Okay, so this is what I said was the first part. We at least have somebody to suspect. And now the second part. And I said that the second part is using Bose-Samuelson varieties. So what are Bose-Samuelson varieties for G over B? I would define them somehow more generally. So suppose that X is as in theorem. So I have a number of PIs. So these are those P1 bundles. Then I take an element in my Weyl group. So let G be an element of the Weyl group X, which is, as we already noticed, the same as the Weyl group of G over B. And I write this as a sequence of reflections, SI1 composed SIR. And to make my life easier, I will denote the sequence I1, IR. I will denote just by I, while I prime will be a sequence which will be by one shorter. I just get rid of one element. Now I want to define inductively the Bose-Samuelson variety associated to this decomposition of this element. So I start with, say, a variety, what's my notation, sorry, which I will call the empty set with a map F empty set to my X. I'm just choosing a point here. So this will be the base of my construction. Then suppose that I define the Bose-Samuelson for a shorter sequence. I'm sorry, this is I prime. I'm get rid of this one. So suppose that I have a map of Zi prime, a map which I call F I prime to X. Then I take the next contraction, PIR, to YIR. And now I know why I usually write it this way. I'm sorry. Phi I prime, Y, this is X, and this is PIR, this is YIR, and I take the composition. I don't call it by any name. Then of course, I take the fiber product of these, and this will be my ZI, and this will be my FI. And since this is obtained by a pullback, and I have this morphism, then this morphism gives me the section. And essentially to be on the safe side, I should use more numbers, but let me just call this pi, and this S, or maybe P. Excuse me?
It's the parameter space of these chains.
Yeah, exactly. Yeah, but according to the order which I chose. So essentially the idea is you start with a point, you look at the first element in the sequence, then you take the curve which passes through the point. There's only one curve. I'm in a very good situation, right? Then what?
Fiber of your P1.
Yes, it's the fiber of the first one. Okay. Then I take the projection. So here was the, say, pi I1. Okay. Then I have the pi I2. Then I take the P1 bundle, which is coming back from this. But I prefer somehow not to look at the varieties, at the image here, but I prefer to look at the, say, at large. Okay.
What is that I?
This is the fiber product.
What?
Once more, I'm making the inductive definition. For empty set, I'm choosing a point, right? Then suppose that I have, for a shorter sequence, I have a map of this Bose-Samuelson variety, which I already defined, right? Then I'm taking the next index in my decomposition of this G, and I have P1 bundle associated to this of X, and I'm pulling it back over Zi prime. And of course I have the morphism, but in addition I have a section which comes from this map here, right, by the universal property of the pullback. Okay. So these are very important varieties, because additively the images of these varieties associated to the elements of the Weyl group generate the cohomology of the, or homology. Mike is not here, so he will not. Whatever I can say, co or homology, and nobody will. I'm sorry.
You will not suspect you of being from us.
Yeah. Good. Now, the claim is as follows. So here, I was very cautious, and I tried to say that there is a more general statement when this is P1 fibration, but this definitely is a P1 bundle because it has a section, right? So you have O of 1. But in addition, you can write, as it turns out, the Zi is the projectivization over Zi prime of the sheaf, well, Fi I think I should call it, where Fi is an extension of this type. Fi is a sheaf over, well, is a rank 2 vector bundle over Zi prime, and this is Fi prime. Fi prime of KIR, and this is 0. I think I should make some observations here. So I call the sequence the relative Euler sequence. Actually, this is the pullback of the relative Euler sequence over here, possibly twisted by some line bundle. Should I make it more elaborate, or should I pass and assume that everybody agrees? The important part is that this extension, so this extension which is associated to this one, defines the pullback of the relative O of 1 or its multiplicity, in case you wonder why it should work out also for not necessarily P1 band, well, in the situation when you don't have O of 1. So this is the extension which lives in the F upper star of K I prime. No, the other way around. I'm sorry. I'm supposed to dualize it, which is good. So this is x over y I r. So this extension is actually the trace of first-term class of the relative of 1 over here.
First, what is x right now?
X is my variety, okay? So, but is the final variety from my theorem?
Standard sort of kind of more general.
Yes. So what I'm doing is I'm just repeating the construction of Bott-Samuelson, which some people here definitely know, but I'm doing this, I'm trying to explain, right?
What is f I?
I'm just getting into it.
What is,
Well, this is,
when you consider x1, there should be two arguments.
excuse me.
x1 should have two arguments.
Okay, oh. Well, the other way around. Well, H1, okay. Yeah, I'm confusing. Well, H1, which I identify with appropriate X1. I'm sorry, thanks a lot for. Okay, so, well, generally, you have this relative Euler sequence, well, for any smooth map, okay? So, just for a moment, let's say F be arbitrary smooth map. That's wrong. Say pi be arbitrary smooth map x to y, and L be arbitrary bundle, right? So I have, say, the sequence of first jets and their evaluation. So this is there are first jets of a line bundle, and this is omega of x twisted by L. So this is the sequence of the first jets. If you twist it by minus L, then the extension class which lives in omega is the first term class of this L, right? So what I'm doing is I'm restricting this to the extension. I'm just taking the extension, which is with the relative one. So this is x over y twisted by L. This is my bundle, let's call it F, and this is L. Okay, so I'm taking the image of the extension under this map, right? From H1 of x into H1 into the relative one. Okay, and then this is the pullback over via Fi. This sequence is a pullback via Fi of this extension for this map. However, since I have this section S,
I'm sorry, what is pi?
once more, I'm sorry.
Pi is this, right?
Yeah, I'm taking this pi IR, okay? So I'm just applying this, pulling back. So here, essentially, it should be I'm taking Fi and applying it to the sequence where this is the relative any line bundle, which is ample over here, but it can be also relative of 1 if I prefer, right? Then I obtain, via the pullback, I obtain this extension. The only difference is that these things over here are obtained as the pullbacks via Fi of the relative k, while I don't care about this one, because this one is essentially, well, it's trivial, right? So I don't care about this one. Once more. Okay, I'm sorry, I'm kind of chaotic.
This sequence, where is it?
Once more. I'm twisting it back to get it O. Right? I can do it, right? Good. Then I'm pulling it back from X to Zi. There is the problem because here I have F upper star I. Okay, so this extension is the extension which lives here. Right, but this is not bad because I have the section, and the composition of the section with the Fi is Fi prime. Right, so I can compare this extension with the standard Euler extension, which is here, And I claim that this is the same as the standard order extension now. So I can put fi prime here. And this sheaf is defined. So this is the sequence over zi prime. That's the deal. So what I'm saying is, I have a way to construct Bose-Samuelson via the following data. I have a variety with a number of contractions, which are P1 bundles. And I'm define these inductively, but essentially the inductive step is encoded in this thing.
But what is Bose-Samuelson?
Well, this is, let's call it Bose-Samuelson for X, where X is my variety for which I...
Is it somehow a bundle over X?
No. No, well, okay, once more. I start with, well, so Bose-Samuelson depends on the composition of an element in the Weyl group into reflections. Okay, so on a formal sequence, but I know that this formal sequence, and this is why I recalled all this general stuff about the relation of the phases and the Weyl group, etc. This sequence is associated, each element of this sequence, I'm sorry, is associated to a P1 bundle, right? Then it is recovering an object by a consecutive, like, tower of a P1 bundles, okay? So Bose-Samuelson in the standard way for a flag variety are constructed exactly this way. So what I'm saying, that I just whitewashed the G over B, and I'm just thinking about this variety over here, right? And I'm constructing Bose-Samuelson. Now, the important part is that inductive step of the construction actually is controllable right now, okay? It is exactly controlled by this object here, right? So, and moreover, we also notice that this is a relative Euler sequence, so it encodes the first Chern class of the relative O of 1. So this is supposed to be non-zero if this previous Bose-Samuelson contains fibers of this map. Because when restricting it to the fiber, this extension, this element defining this extension will be the first Chern class restricted to this fiber. Okay? So I will be good. Well, okay, now let's reveal the whole strategy of proving this. The idea is as follows. We start with the outcome of step 1. So we have formal...
Excuse me, can you repeat the last step about each one?
what I said. Yes, I agree. That's important. That's okay. So what I'm trying to say, that the construction is inductive, but somehow the next step is already encoded in this extension, which is the H1 group, which I will then, the major technical part will be to understand what it is. But here I just want to say one observation, that this extension as an element here is the pullback of the first Chern class or its multiple of the relative O of 1. Pullback to the Zi prime. Okay? So if by any chance Zi prime is mapped here so that it contains the fiber of this map, then this cannot be 0. This extension. If it contains some fiber, because then I would say, okay, I restrict this sequence to this fiber, and this did Atiyah extension for the O of 1 on this fiber point. So this is non-zero. Okay, so here is the idea of how to finish the theorem, how to prove that. So if by any chance we could prove that Bose-Samuelson are unique,
Unique, you mean independent on the choices of your order?
yeah. Well, no. I'll be very specific just in a moment. Okay. Okay. So now remember that these Bose-Samuelsons were associated to the decomposition of these elements, and I have a particular, the longest element here. And for the longest element, I said just in passing that the longest element should define the the canonical class in the homology or cohomology. Don't make me distinguish these two things. So in particular, for G over B, this defines a surjective map. Okay? So if I take this longest element, so I take Bi, where I is associated to the longest, this is the longest word in the Weyl group of G, not B, Zi, then it is known that the map from this to G over B is actually birational. These varieties, by the way, were very important to understanding the homology classes, understanding the singularity of the homology classes, etc. Okay? So suppose that I can construct all the way isomorphism of, this is Z of I for G over B, but suppose that I can construct the isomorphism of Zi, of the same Zi for my X. Okay? And it comes with this map, this is Fi, to X. Okay? Then from what I know, right?
Zi is constructed by X.
I'm sorry.
Left Zi is constructed.
Left is, this is the X construction. So these are the apparent Bose-Samuelson, and these are the true Bose-Samuelson. Now, unique means that I want to control the construction of this Bose-Samuelson at every step, and suppose that I can control so that I get to the longest word. I mean, this part will be tricky because for some you can, for some you can't, and yeah, I will explain it in a moment. But suppose that you can reach the highest level, right? Then what you know, you know that this is birational. The pullback, remember that you have the isomorphism of these objects, and actually the construction here will come with the identification of the relative tangents for both morphisms. So from the point of view of the cohomology over here, the pullbacks of line bounds from here and here are the same, right? So in particular, I will have the Stein factorization from here to here. Moreover, the canonical are also the same. No, this is smooth. I mean, G over B is smooth.
In Zi, so there is Picard is different, right?
Yeah. The Picard is different. I mean, no. The pullbacks of line boundary from here and from here over here are the same. So in particular, if I take an ample bundle, say over here, then this is the same as the pullback of a line bundle, ample line bundle over here, right? Therefore, I have these two maps, but this map is birational. Therefore, the Stein factorization of this map must go through this here, right? I mean, the pullbacks are the same, so things which get contracted in both maps are the same. And this is birational, so this is somehow most economical. So maybe here I have a finite map, but the canonical divisor, I'd said at some point of these two guys is the same, and it was mentioned not a long time ago that since this is well, whatever, Fano or an étale map of two Fano is supposed to be isomorphous, and I would be done. Okay, so the whole trick is that we want to recover these Bose-Samuelson up to the, well, actually I don't care if I can, first of all, I don't care that this should be unique for any sequence. It may happen that it is not. Secondly, I don't care that for every element this is the same. But maybe I can find the sequence of the reflections so that at every step I will have these two guys, both for x and for g over b, the same. Then I will walk up all the way to the top one, and I will use this argument to prove that they are isomorphic. Right? Yeah, sounds okay. I don't think it's cheating.
What the uniqueness mean? What the uniqueness mean? Is it, does it mean?
Well, I have isomorphism.
So how about isomorphism upstairs?
You mean this one? This is what I'm about to prove. Yeah, this is my statement. If I can prove, this is the word unique, then I have the isomorphism over here. Okay? Okay, and the word turns out to be complicated. So, essentially, the best statement which can occur is, so best that can expect is that for every g in the Y group of G, there exists a presentation of G I1, sigma I1, sigma IR, such that now I will refer to this setup. H1 of F upper star IS omega x over IS plus 1 is 0 if IS plus 1 is not in I1 up to IS, 1 otherwise. If by any accident, well, which means that if for any element in the Y group I have a presentation in terms of the reflection, so that whatever, I should say, S bigger or equal than 1, smaller or equal than R, such that for some S, this step, which I do here, is unique, and I said that if I use this reflection, therefore I use this contraction just a moment ago, then the extension is supposed to be non-trivial, right? Which means that this is, then I'm supposed to choose the non-trivial extension. And this says that the first extension is just trivial, as you may expect. Okay, so this is the best which you can expect. Okay, so the life is complicated, as it turns out, because it turns out that the best cases occur. So the best cases is when this is true for Dynkin diagrams with no multiple, so A, D, E, no multiple edges. Well, then I said, okay, I don't insist that for every G, but at least for the G maximal. Okay, so true for a presentation of G max for B and C. And guess what? There is no presentation for F4 and G2. Well, the case G2 was done by Watanabe some time ago. The case for F4 is a funny thing because the paper with this two-step argument would be, well, I think like 40% shorter, if not the case F4, which requires completely different argument. Well, not completely, because we use shorter diagrams too. But at any rate, it's really the pain. Okay, I'll explain how to prove these statements, and essentially I'll try to explain how, why this case is much easier and why this works. Unless you will kick me out, will you?
No, it's, there was a case when the seminar went on until 1:30.
No, don't expect that. I'm the first speaker tomorrow morning, and I can already hear.
The second half is informal. Everybody can have some tea or leave or whatever.
Okay.
Feel free to.
Okay, so that's the technical lemma. I'll stay with this. Well, maybe I'll stay with everything except this one. This is not needed.
So just so you understand that when you erase, that allows you to inductively identify the ZIs or the Schumann B.
I'm sorry, I don't.
I mean, the thing you just erased on that board, the identification of these invertible sheaves step by step on the ZIs,
Yeah.
that allows you to prove inductively
Yeah,
the isomorphism between
Yeah,
the ZIs for
yeah.
X and for Schumann
yeah,
B.
yeah, exactly. 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 Well, they depend very much on the presentation of a word, right? So the whole, okay, so the whole theory is that their image are the Schubert varieties which generate homology of the flag variety. And then they were used to prove certain statements about these Schubert varieties which are somehow canonical. They are coming. They can be described also in different ways, right? But they have very nice properties which are actually used in the proof, but I will not explain them because it would take, I don't know, another. So, but if you are asking about, you want to have some factorial properties or what?
No, I'm asking about presenting this as a modularized space or something. Then you would probably have something like the universal object. And then it would be easy to correct that.
Okay, vaguely I may guess that, okay, so everybody talks about the chain of rational curves, and here we have a directed chain. So maybe there is a good notion for these objects, but I didn't think about it, okay, so this is not really the question that I considered. Okay, so let me explain how it works. So essentially, this should be standard, except that it is more or less technical. So in the setup here, so we want to consider the pullback. So I said that we want to understand H1 over Zi of the f upper star I of k I r. Okay, but essentially what we want to understand is perhaps slightly more general picture. Namely, we have a line bundle L, which is over X, and we want to understand how cohomology of this looks like, of the pullback over Zi. But this pullback suppose that I have this sheaf Fi, so Fi equals F, and I can think about this as so this is rank 2 vector bundle whose projectivization is the Zi. So I have a divisor class associated to this Fi. Let's call it H. Hi. This is O of 1. Well, so this is the thing such that F, the projection of Hi is this Fi. And I can write this thing as, say, R time Hi plus pullback via pi of what? Of some line bundle. I don't want to screw my notation, so yes, okay. Yes, I know what. I want to write it as pi. I want to explain this. Pi upper star of Fi prime pullback Al. Ta-da. Why this should be true? So I claim, so look, it may be somehow strange, right? Because what I'm saying is on the left-hand side you have one object and on the other side you have the same object and something extra appearing here. But the difference is this Hi, which has this property that Hi restricted, so the pullback via S, so restricted to this section, it has the section, is just O. So first of all, a general statement is that, that I can write it this equality in this way, right? Time the pullback of some line bundle. Then I apply S upper star to both. Then I realize that this thing which I driven here is actually supposed to be F upper star I prime. Okay. Gosh. Okay. So the technical lemma is as follows. Let me consider only the case. Suppose that R is bigger or equal than 0. Otherwise, use the duality. Bigger or equal than -1, okay? Otherwise, duality. So first of all, the cohomology of such a bundle, all cohomology vanishes if R equals -1. This is clear. I mean, if the restriction of a line bundle to the fiber of a P1 bundle is -1, then first direct image and the 0 direct image is 0. Okay, so I may assume that R bigger or equal than 0, and then the push forward of this, so the Hi I'm sorry, Zi of F upper star L equals Hi of the push forward of this, which is over Zi prime, and this is SR, this is the symmetric product of Fi. This is the sheaf which lives over Zi prime, twisted by the pullback I prime of the same L.
So in which situation is this lemma?
Suppose that I have a line bundle over X, and I have a sequence, a construction, inductive construction of Bott Samuelson, right? Then what I'm saying with the notation which is above, the cohomology over Zi, which I will calculate, I can express in terms of the cohomology over Zi prime at the price of considering twist with the symmetric one. But the important part is that I have the presentation of this I, therefore I have a filtration of I have filtration of this vector bundle in terms of, so this, let me be vague, so this depends on the cohomology of F upper star I prime L, and I have F upper star I prime of this KIR, okay? But to the rth F upper star I prime KIR, and here I should put, say, I'm using R, so let this be S, for S equals 0 up to R. Because if I take this, the R symmetric power of this, then it has the filtration in terms of the powers of this line bundle, right? Okay. So I have an inductive tool now to calculate the cohomology. And now this, the case where the Cartan matrix has no numbers bigger than 1 outside of the diagonal. It's obvious, because then you don't have this thing growing. Essentially, you have only at most 2 values which you are supposed to consider. If you have multiple, I mean, if you have 2 outside of the diagonal, am I supposed to explain this? I'm sorry. Maybe I was too quick. I should understand this thing, okay? This has the negative intersection, so I'm supposed to do the duality with respect to the canonical. The duality I'm supposed to understand in terms, again, of the Cartan matrix, and this is my first step. Then I'm finding the cohomology of a line bundle L, but now down there, so this is the previous step. There was some confusion here. No, it was, no, after dualization, the previous step. So this is KIR, so it has outside of, if I don't have multiple edges in the Dynkin diagram, the calculation of the cohomology over here, yeah, once more, I'm sorry. I'm supposed to calculate this cohomology, okay? Then I'm descending, so I'm not treating this object as L in my lemma, but I'm taking the object which is obtained by the third duality, okay? Then I'm pushing it forward. Then it turns out that usually, unless this contraction, this previous contraction is associated to the I, which has I R minus 1, which has non-trivial intersection with the previous IR, I can go on, because I will have all, in this case I will have 0. If I have 1, then I have 2 things appearing here. But fortunately, in this case, the 2 edges in my Dynkin diagrams will be adjacent, so actually the difference between them, which is the sum of the appropriate canonical, will cancel the -2 which appear here. so which is good. And that's why I obtain eventually the vanish. I'm sorry. It's, I have the impression that, first of all, you are tired, but more important, I'm tired. And the more I will explain, the more we will have the impression that it's complicated, but it is not. Okay, I mean, this is the technical observation. And from this point on, this is just calculation, right? So it may be harder or not. The point is that in case of no multiple edges, you get more or less immediately you get the claim. In the case of the multiple edges, you are supposed to choose the decomposition of the element in appropriate way, so that you don't run into the situation that this filtration will multiply. And it turns out, and it was a computer search for F4 in particular.
The bad situation when if you have two vertices in your decomposition of the word, if you have two reflections corresponding to double edges.
Yes, but
A representation of W0 in order to avoid this.
yeah, the point is that you are supposed to choose. So suppose that you are in the case of the B or C diagram, right? So you write the longest word and you make the the construction of which is the calculation of this cohomology. The bad thing is if your word will contain somehow this edge several times, because sooner or later you are supposed to go through all this through all these edges, right? I mean, they are the generators of your group, so no way that you can avoid the bad situation. But at least you can choose the word in which you can control the behavior of this step when they are close, right? That's roughly the idea. And it turns out that the F4 is just wrong. I mean, there is no, we run the computer search if you can actually prove that this will vanish, and you don't have, the statement is just wrong for F4. So if you believe that you have the unicity of the Potsdamer for F4, then this is not true. My guess is that this is related to some special singularities which may occur for the Schubert varieties for the F4. So in order to make these cycles to be good, when you have more possibilities, because this H1 is not what you expect, you are supposed to choose one of them, a special one of them, which will make the singularities, well, of the type that you expect. But as I said, the case of F4 is technical. Essentially, it uses the calculation for C3 and B2 and the go-down construction, so the contractions, etc., etc. Okay, as I said, I think that we are all. Thank you very much.
Thank you very much. And there are maybe some questions, comments.
Is there any opportunities for not complete flag writing for Gmod?
Well, the same argument won't work because you don't have the while group. That's nice. Okay, so the strategy for these will be to rebuild the thing. So there are two approaches. Either to climb up in the cotangent bundle. So this is the approach using the varieties of minimal rational tangents. So essentially the tangents live in the projectivization of the cotangent bundle, right? And the problem is that the parameterizing varieties for homogeneous varieties, for some are not homogeneous anymore. So you are supposed to choose, there is the group acting, but you have some open orbit and some closed orbit. So you are supposed to be, if you want to run the inductive process by going up, then you are supposed to distinguish somehow a subset of rational curves. And now, no tricks like this one. You are supposed to choose the curves over which the tangent of the incidence variety will be satisfying the group property like being nef. And we don't know how to overcome this. The other way is to relate it dually to the question of symplectic geometry, because does it make much harm if you assume that this is nef and addition big? It does not, right? Then you have a symplectic contraction of the total space of the tangent bundle, or the contact structure and the contact contraction of the projectivization of the tangent bundle. And right, that's another approach, to look for the homogeneity there. So far, the thing that we've been working and somehow are the questions, the relative questions. So you would like to have something which looks like a bundle of homogeneous varieties, and you want to understand if, say, having two contractions which are homogeneous, you can rebuild a homogeneous variety which dominates them, and what are the conditions. So it would be the intermediate step which you would need to making this going up construction. And this apparently works.
I guess not. Thank you.
Thanks.